Hello everyone, I'm going to record a presentation on the AQFP superconducting-based deep learning acceleration. So let's start this presentation. So the outline of this presentation is shown here. First, we're going to discuss about the AQFP basics and also the logic synthesis. And then we're going to discuss about the AQFP physical design flow, including the placement and routing. And after that will be the stochastic computing-based AQFP deep learning acceleration framework, which is our ISCA paper last year. And then we'll discuss about experimental results, including the actual tapeouts and conclusion. The actual tapeouts is done by Yokohama National University. So here is the basics of the AQFP logic cells. So the most basic logic of the AQFP circuit, superconducting circuit, is actually a buffer. This is a structure of an AQFP buffer. And this buffer, with the details shown here, is actually uses two Josephson junctions. And this AQFP buffer, we can have the connection, the parallel connection of this kind of buffers, and then we can implement different logic cells. For example, a majority cell is shown here, an AND gate, a NOR gate, a splitter is shown here. So all of those splitters and also other gates are based on the AQFP buffers. So the logic gates are all based on the majority gates. You can see for the NAND gates, for the AND gates or OR gates, it's like majority gates with one of the three buffers changes to constant 0 or constant 1. So actually the majority-based gates, including the majority, minority, and other logic gates, will be the most efficient one. So actually the AQFP logic circuits, this is driven by the AC power. And this AC power will also serve as the clock to synchronize the gate outputs. So we can see this is an example of the four-phase AQFP logic. The four-phase is a standard one. Here is phase 1, phase 2, phase 3, phase 4 of the clock, and then it is phase 1, phase 2, phase 3, and phase 4. So the logic, the data is going to come from the top one, and then we're going to go through the computation layer by layer. So this is like a deep pipeline structure. We can see from here the phase 1 is computing in line 1, and phase 2 is computing in line 2, phase 3 is computing in line 3, etc. So for each of these phases, actually there is an overlap of half of the phases. So, and then the data can propagate from the top to the bottom. So because this is a deep pipeline structure, it needs to be perfectly path balanced. That means all the inputs to any gate must have the same delay from the primary inputs. The data is actually arriving at the phase 1 simultaneously, arriving at the phase 2 simultaneously, phase 3 simultaneously. So for each of the inputs of the same gate needs, and for arbitrary passes needs to have the same delay and same number of clock phases. So the majority-based gates, including the 8 types of majority-based gates, including the majority, minority, and also we are flexible to add the inversions. They're actually very efficient to implement in AQFP. Actually, in AQFP, you can see all the other logic gates like AND gates or NOR gates or OR gates, they're based on the majority-based gates. We can see some of the examples of the majority-based implementation versus the AND or inversion AOI-based implementation of a full adder. This shows an example. The top one is actually the majority-based implementation based on the majority gates. And the bottom one is actually the conventional implementation. We can see all of these buffers are needed because the AQFP needs to having the balanced signal, the path balancing. And those splitters are also needed when the fan out is more than 1. So whenever there is a fan out more than 1, there needs to have a splitter. And this splitter also takes one phase, one clock phase. So this further increase the number of gates, the Josephson junctions and also the delay. So when we compare the top one and the bottom one, we see that there is a huge difference. The top one only requires 34 Josephson junctions, and the bottom one requires 102 Josephson junctions. So we can reduce the number of Josephson junctions by 3 times and reduce the delay by more than 2 times if we change to majority. So this is the reason that we have built a flow of majority-based synthesis and the optimal buffer splitter insertion for the AQFPs. So the input is actually integrated with the uses. We use a logic synthesis to get an efficient and/or implementation of the circuit logic. This is AOI based, and then we are going to have our own majority netlist conversions, and then it becomes a more efficient majority-based implementation. And after that, we are going to perform the buffer and splitter insertion. So the buffers are for the path balancing, and the splitters are for the fan out with more than 2. So, and finally, it is a netlist that is ready for placement and routing. We see some of the results. This is actually a result of an entire RISC-V ALUs. So this is actually, we have logic codes, and then after we synthesize it. If we are using the conventional design instead of the majority-based design without optimizations on the buffer splitter insertion, we can see the Josephson junctions, number of Josephson junctions is over 75K, and the delay is 172. So with our full optimizations, including the majority-based optimization, and also the buffer and splitter insertion, with all of this, we can see we reduce the Josephson junction count by 3 times, and we reduce the delay by about 2 times. So here, we can see the significant difference. And if we compare with another technology, the RSIQ, which is the conventional, the most standard technology, which is a DC-based superconducting electronics, and we can see that the AQFP also has an advantage of the Josephson count by about a factor of 2. The reason is because the majority-based implementation is quite efficient. So this is one of the advantage of the AQFP compared with the other superconducting technology. So using the synthesis results, we can perform the physical designs. The physical design including the placement and routing. We have developed an AQFP specific placement and routing framework. For the AQFP placement, we use an iterative layer-wise determination from the layer with the largest total cell widths. So the row-wise placement algorithm actually has a polynomial time optimal solution. And for the AQFP routing, we have adopted the negotiation-based A-star search algorithm as a backbone, and we have optimized for the AQFP technology. It's actually going to rip up and reroute each net in an iterative manner. At first, sharing of the routing resources will be allowed. And then we're going to gradually increase the congestion cost, and the net needs to negotiate with each other for the routing resources, and then this can avoid the potential NP completeness. So it avoids the potential rip up and reroute procedures. So we can see the experimental results. So we use the estimated the half parameter width and length HPWL as the optimization goal as the estimated cost. And actually we compare both the estimated value, the estimated cost, and actually the actual routed wire length. We can see our proposed placement algorithm can achieve a significant reduction in both the estimated total wire length cost and also the actual wire length after the routing procedure. Actually, this reduction is from about 13 times to almost about 50%, sorry. And then if we can consider the number of routing tracks, we can see that the proposed physical design framework is also reduces the number of required routing tracks between the cell rows. And in this way, we can also significantly reduce. This is also attributed to the placement. If we consider the routing with the best possible placement results obtained by our frameworks, we compared with the left edge based routing algorithm for this kind of channel routing, because this is a phase 2, phase 3, and then each of the cell is actually row based. And we're going to routing in the middle, and we can also routing on top of this kind of cells. And we're going to compare with respect to the number of additional tracks in addition to these cell rows. So if the number of additional tracks is 0, it means that we can achieve the minimum total height. We can achieve the minimum height here. So we can see for many of the cases, our proposed routing can achieve a track number of 0 additional. So it means that it only needs this given rows. It does not need additional tracks in between these rows, cell rows. With 3 of the routing cases, actually we need certain additional tracks. But we can see the routing time is okay. The maximum routing time is about 6 minutes, which is quite good. We can see that this kind of our negotiation-based routing algorithm can significantly reduce the number of routing tracks. So the routing plays an even more important role than the placement in the result enhancement. And we can see some of the sample routing placement and routing results. Here is the placement and routing results of a 32-bit bitonic sorter. As we'll see later, this kind of bitonic sorter is a key part in the neural network deployment. And this is the 3D structure of one-channel routing results. And this technology is from the MIT Lincoln Lab. So this has 2 routing layers, and actually there can be the wires connected in between. And there are more placement and routing results, and this is a partial results of a 32-bit RISC-V pseudo-core ALU, and this is only the partial, and then in total there will be more than 100 rows. So we have the synthesis and physical design framework. So it means that as long as we have a circuit design, and then we can transform it to synthesis to the netlist, and then we can generate the GDS2 files, and then that's ready for the actual tapeouts and testing. So then we're using one example of the deep learning acceleration to discuss about our circuit designs and what will be the suitable circuit designs examples for the AQFP superconductor. So actually this stochastic computing, this computing scheme can be quite useful for the AQFP superconducting systems. In stochastic computing, a number, or named the stochastic number, is implemented using a sequence of the random 0 and 1s. So what is represent is actually by counting the number of 1s. For example, in these dreams, there are 3 1s out of the 8 0 and 1 bits. So this represents 3 by 8, which is 0.375. If we want to multiply 2 of the stochastic numbers, then there is a stochastic number on top, and there is a stochastic number at the bottom, and these two only needs to go through an AND gate. Because for each of these, the 1, and then it will encounter one of the value 1s in the bottom stochastic number with a probability of 6 by 8, which is 75%. So you can see this kind of stochastic computing is using the independent bits in each clock cycle. And also it has a very small hardware footprint. So for each of the clock cycles, it's independent with the previous clock cycle. So this kind of structure is very compatible with the deep pipelining nature of the AQFPs, and the control is much simpler. Although the AQFP has a deep pipelining nature, and also it has a very low hardware resource utilization, which is also suitable for the AQFPs. In our previous work, which is in the SPLOS 2017, we have developed a stochastic computing-based deep neural network acceleration framework using the CMOS technology. So here, we are using an inner product, and we are having designed a so-called approximate parallel counter, or APC, for the additions because it is more accurate compared with an adder trees. And then we have designed the activation functions. We are using the finite state machines for the activation functions. Previously, the tangent H is actually one of the very much matured activation function using the stochastic computing. But because most of the current deep neural networks are using ReLU, so we have extended the activation function to support sigmoid, to support ReLU. So those are all the works that we have done using the stochastic computing, and we are one of the earliest to work in this domain. But those kind of technique may not be that useful for the AQFPs. So we have developed a stochastic computing-based accelerator for using the AQFPs. So we have designed the innovations of the implementations of individual blocks for the stochastic computing. We have designed novel feature expression blocks that integrate the summation and activation into a single logic block. For the pooling, we have developed a sorter-based sub-sampling block that is much more accurate compared with the previous multiplexer-based one, and it is very suitable for AQFP. And for the fully connected layers, we have developed a simple majority chain block for the fully connected layers or for the classifications. And this one got accepted in ISCA last year. So this is an overview of this AQFP-based deep neural network framework. The inner product and activation functions, which is the multiplication and accumulation in the deep neural networks. Actually, in AQFP, we are using a partial feedback sorters. For the poolings, actually, we also use the sorters, which is a half feedback sorters. And previously, we have already illustrated the placement and routing results for the sorters. And for the final fully connected layers for classifications, we are using this kind of majority chain-based structure, which is majority-based, also very suitable for the AQFP technology. Actually, for the stochastic computing in CMOS, there is one big hurdle, which is the stochastic number generation. This requires the true random number generation, or at least pseudo random number generation. So generating random number is quite burdensome for the CMOS-based implementation, but this is quite straightforward if targeting at the AQFP technology, because the AQFP buffers can serve as 1-bit true random number generator. And the stochastic number generator actually requires this true random number and one comparator. And then we have implemented a comparator here. And we have further developed a structure that can generate an array of random numbers that can be quite efficient for the AQFP. So in a nutshell, we're going to say that this kind of random number generation blocks is really highly efficient in the AQFP and much more efficient compared with the CMOS-based implementation. So for the bitonic sorter, we're using a bitonic sorter because this one is an ideal structure for the AQFPs. And it is quite useful, and it can implement an approximation of the multiplication and accumulation, and also the activation functions. This structure is ideal for AQFP because all the signals having the same delay, and all the signals are duplicated at each stage. So the fan noise is the same, and also the delay is the same. So there is no need for additional buffer. So the design can be quite beautiful. So this is actually the block diagram of the Bytonic sorters. And later, we can see how we implement, decompose, and implement a Bytonic sorters. This is a scalable design that a larger Bytonic sorter can be implemented using two smaller sorters together, and it can be quite efficient for the AQFP technology. For the feature extractions, actually we have implemented the feature extraction block, which is a multiplication and addition using the Bytonic sorter based on the designs with the partial feedbacks. So this is the structure that the input is shown here. Here is going to implement the multiplication of the input and the weights, and here is going to implement these accumulations, and here is the output. So the details why this is equivalent to a multiplication and addition is already shown in the paper, and we are not going to discuss in details due to the limited time. So we can see the inaccuracy, which is absolute inaccuracy. We can see when the bit stream length is increases, the inaccuracy drops. When the input size increases, the inaccuracy also drops in general. We're going to see that this kind of inaccuracy is minor. This is an absolute inaccuracy, and this kind of inaccuracy can be well mitigated after the layers and can be mitigated through the training process. The sub-sampling block over the poolings is also based on the Bytonic sorters. And this is the so-called half Bytonic sorters with the structure shown here. And the details is also shown in the papers, not discussing in details. And here shows the inaccuracy. You can see the inaccuracy is very small. The inaccuracy is even lower compared with the CMOS when it's implemented using the stochastic computing. And finally, this is the categorization block, which is for the fully connected layers. We have implemented an efficient one, which is based on the majority chains. From the input to the output, this can give one prediction. And the output, and this outputs is through a chain of the majority gates, which can be quite efficient using AQFP. So we can see that the errors in these fully connected blocks is also quite small. This shows the error here. So we see the experimental results. We're going to compare with the CMOS for efficiency, and the results are shown in the subsequent slides. And we have also done the physical test to validate the accuracy. So we have built a chip, and it's mainly done in the Yokohama National University, and this is their testing facilities, and is also tested there. So the physical test actually matches with our circuit design, and it shows a good accuracy. So first, we can see some hardware results, the comparison with the CMOS results using the 40 nanometer technology. We can see the energy efficiency of the AQFP and the CMOS, and also the delay of AQFP and CMOS. We can see the delay of AQFP is a couple of times better compared with the CMOS, but the energy, there's a huge difference. This difference is in the order of 10 to the power of 5 or 10 to the power of 6. Actually, this is because the high energy efficiency of the AQFP is almost theoretically almost doesn't cost power. But in fact, is actually cost someone, but is already the most energy efficient technique that is approaching the quantum limits. And for the feature extraction block, we can see the similar results. That is multiple orders of magnitude, 5 or 6 orders of magnitude more efficient, energy efficient compared with the CMOS technology. And we can see here that the delay is also much better because the design based on the Bytonic sorter can be quite efficient. Here for the subsampling, we can also see the results. But meanwhile, we can see that besides this kind of significant improvement in the delay and also in the energy, we also get a higher accuracy in the subsampling or pooling block compared with CMOS. For the fully connected or categorization blocks, also the results are similar. Improvement in delay and energy efficiency. We can see the results in the application. So this is tested on the IMNIST, but we already successfully tested in CFAR as well. So we have implemented one of the fully connected that's ensembles a spiking neural network and also a convolutional, which is a deep neural network. So we can see that the accuracy of the stochastic computing-based AQFP is even higher compared with the stochastic computing-based for CMOS, because the subsampling is more accurate, and also the bitonic is actually more accurate. And the energy can be multiple orders of magnitude better, because it is actually the energy is the key advantage of AQFP, although it has other advantages, but energy is definitely the most prominent one. Okay, so for the conclusions, we have proposed a stochastic computing-based deep neural network acceleration framework using the AQFP superconducting technology. So this is based on the prior work on the AQFP synthesis and also the placement and routing. So we have an accurate integration of the summation and activation using the bitonic sorters. We have a low complexity fully connected block based on the chain of majority gates. We have an ultra-efficient stochastic number generator in AQFP and a high accurate subsampling or pooling block in AQFP. AQFP is very promising for the energy efficiency, and we will continue to investigate the architectures using AQFP for deep learning. So thanks. I'm happy to take questions.